In this video, I'm going to talk about motion graphs, that is, distance time graphs, velocity time graphs, acceleration time graphs of simple harmonic motion. Please take a moment to read the success criteria I plan to cover in this video. So let's first start by thinking about how we can make this time graph. What I'm trying to show here is a pendulum with a pencil at the end, or a marker. And if I just have it like this and I set it swinging, I'm going to get a line back and forth. Remember, a pendulum has simple harmonic motion for small angles. But if I start to pull this paper in this direction, as it swings back and forth, I'm going to move along the paper. And in fact, I'm going to get this as a shape along the paper. Now, if it's moving at a constant speed, that means it's going to make this nice periodic pattern. Remember, it's going to slow down at the edges, speed up, which is why it's moving almost like a straight line, slow down, stop, and then turn back in the opposite direction. So here's my pendulum. Let's say I start over here at A. Now, just like our normal number lines in math class, I've put positive on the right side and negative on the left side. And if I start it over here at A, it's not moving. It's going to speed up and go to C. This is our equilibrium line. Slow down and stop at E. So here's our equilibrium line right here. I'm going to say this is A. When it crosses our equilibrium line, that's C. So B must be in here somewhere. I'm going to get to the very end, so this must be point E, and D will be in the middle. So I'm going from my positive position towards the negative, all the way down to E, starting at the positive position to the negative to E. And now I could do the same thing. It would be D here, C, B, and A. So if I show one complete cycle here on this, I guess it's a cosine curve, would be starting from A and returning back to A. So let's think what's going to happen then at a velocity time graph. Over here at A, I have it at rest. So this is A right here. Now you might think, why do I have this going down? Well, here at A, if I'm moving towards C, this is in the negative direction. So technically, even though my distance or my displacement is positive, my velocity is negative. And I'm going to speed up until I reach here. That is C. I will slow down and I will stop at E. Remember, on a velocity time graph, this is V equals 0. I will then now go in a positive direction until I hit C, which will be my fastest speed, because all of the potential energy here will turn into kinetic, and I will slow down again at A. Notice one complete oscillation, so I get back to the same spot, moving in the same direction. There will be one complete oscillation. If we were doing waves, I would call that one wavelength. So let's compare these side by side. This is my distance time graph, my velocity time graph. Notice when this one's a peak, this one is at equals 0. When I get to the center, at equilibrium position, my velocity is the magnitude of the velocity is a maximum. It just so happens to be in the negative direction here. They are 1/4 of my wavelength out of phase. It just means, as I said, when one's a peak, the next one is 1/4 of the wavelength out. Now you may remember that one of the conditions for simple harmonic motion is that the acceleration has to be proportional to the displacement, and it's in the opposite direction. Now, over here, my displacement is a maximum, and so will my acceleration. Since the displacement is a maximum and positive, my acceleration will be a maximum and negative. Now you might think that seems a little counterintuitive because it's not moving here, but remember what happens as it comes down to the bottom. It's going to be turning its potential energy into kinetic energy. And when we get down here, the curve is very slight. So in fact, I've got very little potential turning into kinetic, making it right here at constant speed. So to go from just a little bit to a little bit faster, a very little, and in fact right here, 0 acceleration. So this will be C. I'll get to the other side. Now notice once I cross here, once I go past C, all of these accelerations are positive, even though they're in the negative positions. So this will be E, back to C, back to A. Now, if I put all three graphs together, my distance time graph, my velocity time graph, and my acceleration time graph, I said that these were 1/4 of the wavelength out of phase. So 1/4 wavelength. Remember, one whole wavelength would have been 2 pi, so 1/4 of that would be 2 pi divided by 4. So that means they are pi by 2 out of phase. In this case, when displacement is a maximum positive, acceleration is a maximum negative, and that was because A is proportional to negative x. So in this case, they are half of that wavelength out of phase, so I can say 2 pi over 2, or I can say they're out by pi. Okay, so let's do an example. I have here a displacement time graph, and I'm asked which statement is not correct. The speed of the particle is a maximum at t over 4. Remember, t stands for the period, the time it takes for one complete oscillation. And at t by 4, it's right here back at the displacement equals 0, the equilibrium point, and that's going to be a maximum constant speed. That is true. It says here the velocity at t by 4, that's right here, and the velocity at 3t over 4 is right here. Notice they're both at the equilibrium position, and it's asking if the velocity is the same at those both places. Now notice this one says velocity, which includes direction. And in this case, it's moving in a negative direction, and here it's moving in a positive direction. It's going up towards positive displacement. So this is not true. That's what we're looking for. Let's just double check these other ones. The magnitude of the acceleration of the particle is a maximum at t over 2. Remember that A is proportional to negative x. So if x is a maximum, so is A. So at t by 2, our displacement is a maximum, so both of them are true. And finally, the restoring force on the particle is 0 at t by 4, right here. And again, if I say acceleration is proportional to the displacement, and F equals ma, I can also say the force is proportional to negative x. Right here, x is 0, so the force is 0. That is true. So which of our statements is not correct? The answer is B. So let's do one more example. Now, I've been using a pendulum so far in this video. Remember, there's lots of different examples, and so I've purposely chosen a mass and spring system here to have something different. We're going to be using this, it says it's initially pulled up by 2 centimeters from equilibrium. So let me just draw equilibrium here and say this was 2 centimeters and it's released. It undergoes 4 oscillations in 2 seconds, and I'm asked to draw a graph. The word sketch is a specific command term. I need to mark on relevant features, and in this case that means I'm going to need to write 2 for my amplitude. This will be -2. I need to do 4 oscillations, and it's going to go up to, it starts at 2 and I need to do 4, so it starts at 2, I need to do 4, and I need to make sure that they're spaced out relatively the same. So I'm trying to make sure I keep my amplitudes the same. That's about as close as I'm going to get drawing on my screen. Now, it took 2 seconds, so I'm going to label this 2, label this one 1, and that would be an appropriate distance time graph. It says mark with an X the position of maximum velocity. I could do that anywhere along this displacement equals 0 sign, and a constant speed, and any peak or valley would do. So please take a moment and read the success criteria for this video. I hope now, after you've watched it, you can say yes to this point.